Welcome back to Very Ordinary Differential Equations. In this lecture, we complete our review of power series. Remember, this isn't meant to be a comprehensive overview of everything about power series, but rather just a quick review. Suppose we have a power series that has some radius of convergence r. So we write our generic power series as the sum of ai times x minus c to the I. Then we can compute derivatives of f of x and also antiderivatives of f of x, sort of in the best way we might think we could. So for example, the derivative f prime of x would simply be d by dx of f of x written as a series, but rather than taking the derivative of this sum, we can instead take a sum of the derivatives. And individually term by term, d by dx of a power of x minus c to the I is just going to bring down that power and reduce the power by 1. Now notice, when I is 0, we have a sub 0, and then x minus c to the 0 would just be 1, so it's just a constant term. The derivative of a constant is just 0, not something to the minus first power. So if I equals 0, this formula here doesn't work, but rather the derivative of the constant term is just 0, and I can kind of throw it out. So this sum for the derivative starts at a different index. It does not include index 0. If I take the derivative of the index 0 term here, I should just get 0. So I simply ignore that term and apply my general power rule for differentiation to terms of index 1 and larger. Similarly, I can anti-differentiate the power series by instead anti-differentiating every individual term. And this is more straightforward, okay? So I have a constant times x minus c to the I, which I anti-differentiate as constant over I plus 1, x minus c to the I plus 1. However, I do have to add some constant of integration in. I don't need to add a different constant for every term. This plus c is not in the sum, it's just added at the end. Okay, so observe, just to say again, the derivative f prime starts at a different index, okay? Also, both power series no longer have the power of x matching the index I. So both of these are typically going to require reindexing to be of any use. And since we're really intending to use this for differential equations, we're more interested in the derivatives rather than antiderivatives of power series. So for our first example, let's find a power series representing 3y double prime plus y, where y is this generic power series here, the sum of ai times x to the I. Since we're going to take two derivatives of y, we're going to split off the terms of x to the 0 and x to the first, because their second derivatives will just be 0. So the original power series, I'm going to split off the terms corresponding to index 0, a0 x to the 0, and 1, a1 x to the 1, and here's all the rest. Because we can take two derivatives of every term now. The first two terms just have derivative 0, but after that we're going to have a generic power rule coming in. The first derivative brings down I, the second I minus 1, and overall we've reduced the power by 2. If I multiply this by 3, here is a power series for 3y double prime. We ignore those zeros. Okay, the terms for index 0 and 1, their second derivatives vanished, but everything after that will just obey this formula here. So here are the power series that we have for 3y double prime and y. But to add them together, we need the powers to match. So we're going to need to reindex the power series for 3y double prime. And we do it as such. So originally this series would start at index 2, meaning our first power of x would actually be x to the 0. So instead, we're going to start our series at index 0 and make that the power of x. But then I need to change every other instance of I. A sub I, that index is 2 larger than the power. So if the power becomes I, instead of having a sub I have a sub I plus 2. It needs to be 2 larger than the power. Here I have an I minus 1. That's 1 larger than I minus 2. So when the power has become I, that term becomes 1 larger, I plus 1. Here I have an I, which is 2 larger than the power. So if the power is I, this term becomes I plus 2. And again, if this is still fairly new to you, simply start this series at 2 and write out the terms corresponding to I equals 2, I equals 3, I equals 4, and so forth. And then start this one at I equals 0, I equals 1, I equals 2, and so forth. And you'll see you're writing exactly the same thing. But now I have a series for 3y double prime that starts at index 0 and also has x to the I. So here's my new series for 3y double prime. Compare it to the original series for I and notice that both of them go from index 0 on to infinity, and both of them contain x to the same power of I. So we can add them together very directly. 3y double prime plus y. Because they both have the same range of index and both have an x to the I can factor it out of that sum. So we have 3i plus 2i plus 1 ai plus 2 times xi plus ai xi. So 3i plus 2i plus 1 ai plus 2 times xi plus ai times x to the I. So here we have a power series that represents 3y double prime plus y. After re-indexing the power series for 3y double prime, we were able to directly add them. For a second example, let's find a power series for 2y prime plus x squared y, where y again has this generic power series representation. Well, we can pretty quickly take a derivative. Notice that this sum now starts at index 1, because the original series at index 0 is a constant term, and when I take a derivative, that vanishes. But for all the other powers of x, taking a derivative is just the power rule, so the derivative of x to the I is I times x to the I minus 1, and we're also multiplying by 2. X squared times y, on the other hand, if I refer back to the original power series for y, if I were to multiply by x squared, I could bring the x squared inside the sum and simply raise the power of all of my x's by 2. So both of these are going to need to be re-indexed so that the power of x matches the index in the sum. So here was our series for 2y prime. If I want to re-index this so that I have x to the I, this begins with x to the 0. When I is 1, this has x to the 0. So I'm going to start my sum at 0 and have x to the I. And then I look at all the other instances of that index I, here as a subscript and here as a factor. These i's are 1 larger than this power. So if the power became I replace them with I plus 1. What about x squared y? Well, I could just index this from 0 to infinity, but my power is wrong. So notice, if I want the power to be given by the index, it starts at 2. When this series starts at index 0, the power of x starts at 2. So let's start the series at index 2 so that I can use that as my power. Now I have to change all other instances of the index. There's just this one, and it is 2 smaller than this power. So if the power is I, this index should be a sub I minus 2. So here are the series for both of them having been re-indexed so that both have the same x to the I. We can't directly add them together because the second sum does not contain terms for index 0 and 1. So for index 0 and 1, in the first series, we're going to split those off manually. So here was our series for 2y prime, and we need to take the terms for index 0 and index 1 and break them off manually. For index 0, we would get 2 times 1 times a1 times x to the 0, 2a1. For index 1, we would get 2 times a2 times x to the first, 4a2 x to the first, and then every other term is represented by going from index 2 on to infinity. X squared y already had a sum that began at index 2. So now we can simply add these together. So here are the series that we've derived for 2y prime and x squared y respectively, where we've done some re-indexing and some other work so that the sums have the same range of indices and the same power of x. So now we can add them directly. These terms here are just manually hanging off, but otherwise we have a sum of 2i plus 1 ai plus 1 x to the I, 2i plus 1 a sub I plus 1 times x to the I, plus ai minus 2 x to the I, plus ai minus 2 times x to the I. So we've represented 2y prime plus x squared y as two terms that manually sit there, plus a series that begins at index 2. We can attempt to reincorporate terms so that this sum can start at index 0. Well, if I were to let I equal 1 here, we would get 2 times a2 plus a sub negative 1, x to the first. So I would have 4 a sub 2 plus a sub negative 1 x to the first. Compare that to 4a sub 2x by itself. If ai minus 1 is 0, then we would conclude that everything works out. 4a2 plus ai minus 1, if a sub I minus 1 is declared to be 0, would just be 4a2. And then this formula for index 1 would exactly match the 4a2x that our series is supposed to have in it. So we can take this series and simply declare a sub negative 1 is 0. And then we can absorb this term into the series. If a sub negative 1 is forced to be 0, then this formula accurately predicts 4a2x for index 1. We can repeat the same argument to try to see what happens at index 0. All right, so here is our series. What we're going to do is we're going to look at the predicted formula for index 0 and compare it to 2a1, the actual term with x to the 0 in it. Now, if I were to equal 0, in our sum, we would have 2 times 1 times a sub 1 plus a sub negative 2 times x to the 0. But what we wanted to get out was exactly 2a1. So here we do get 2a1 plus a sub negative 2, and we want that to equal 2a1. So again, we see if we set a negative 2 to be 0, then everything works out just fine. So if I declare a negative 2 to be 0, I can take this constant term and say it does actually match this formula. So overall, we can say that 2y prime plus x squared y is just this series where the index goes from 0 to infinity. However, at index 0, this is going to have a sub negative 2, and at index 1, this is going to have a sub negative 1. So we simply declare that those both take value 0 because that was what we figured would make this formula match the missing terms anyway. For a third example, let's find a power series for xy double prime plus 3y prime minus y, where y is our generic power series ai times x to the I. Well, first let's start by taking some derivatives. If I take two derivatives, the terms corresponding to index 0 and 1 will both vanish. Their second derivatives will be 0. Past index 2, however, I can apply the power rule. Two derivatives of x to the I will be I times I minus 1 times x to the I minus 2. Multiplying by x will increase the power of x by 1. So now that power of x is x to the I minus 1. So now we have a series representation for xy double prime. But we know in advance we're going to want to re-index this so that the power of x is the same as the index. If this series starts at 2, but it's being reduced by 1, then the first power of x is just 1. So I'm going to start the series at 1 and make that the power of x. Now I just need to change all other instances of the index. This one matches the power. So here it was I and it's I again. This is 1 larger, so now it's I plus 1. This is 1 larger, so it's I plus 1. So now we have a power series for xy double prime where we've preemptively re-indexed so that it has x to the I. Next, we want to address that middle term, 3y prime. This is pretty straightforward. We just multiply by 3 and take a derivative. So we've thrown out the term corresponding to index 0 because its derivative will be 0. Otherwise, we just have 3ai I times x to the I minus 1. And again, we know we're going to want to re-index this. At index 1, x has a power of 0. So we're going to start it at index 0 and make that the power of x. And then this a sub I and this I are both 1 larger than that power. So if we've re-indexed to have a power of I, those both become I plus 1. So here are the power series that we've derived for xy double prime and 3y prime, where both of them have been re-indexed to have x to the I in it. Note, however, that this top series does not have a term for index 0, but this one does. So we pull out what would happen for index 0. We would get 3a1 times x to the 0, or just 3a1. And then otherwise, we're going to leave all the rest inside this sum, which now goes from index 1 to infinity. So here are the series as they stand now. By pulling one term manually out of the series for 3y prime, what remains are two series with the same range of indices and the same power of x. So we can add them in a pretty straightforward way. This 3a1 hangs off by itself. Otherwise, we just have to add these two together. If I factor out the x to the I, we have ai plus 1, I plus 1, I, 3ai plus 1, I plus 1. So notice we can also factor out an ai plus 1 and an I plus 1, leaving behind an I plus a 3. So altogether, if we factor out the x to the I and factor out the ai plus 1 and factor out the I plus 1, we have an extra factor of I plus 3. So altogether, that's the series we now have. All right, so we've got a nice condensed series for xy double prime plus 3y prime. One term hanging off by itself, and then a fairly concise formula for the rest. Now we just have to subtract the series for y. But again, this series starts at index 1, so we're going to take our original power series and manually pull out the term for index 0 and leave everything else in this sum here. So now I can add these together in a very straightforward way. So xy double prime plus 3y prime minus y. We take this, we subtract that, so 3a1 minus a naught, plus all of this minus that. ai plus 1 times I plus 1 times I plus 3 minus ai. All of this minus that. So here we have our power series representation for the whole expression xy double prime plus 3y prime minus y. Note, in the series, if I wanted to recover the term for I equals 0, in other words, the constant term where x to the 0 is just 1, what would we get? We would get a1, I'm letting I be 0 here, so a1 times 1 times 3, so 3a1 minus a0, which happens to be exactly what was sitting out here. So this term that we manually split off exactly corresponds to what this formula would have predicted for index 0 anyway. So we can just let our series start at index 0 and recover the constant term inside the series exactly as it was written. So xy double prime plus 3y minus y is the sum over all indices from 0 to infinity of a sub I plus 1 times I plus 1 times I plus 3 minus ai times x to the I. So altogether, what have we discussed? Leaving formal proofs behind because we are just doing a quick review. Generally, we just presume that given a power series, you can differentiate it and integrate it without much thought. Then what you can do is you can determine simplified formulas for various combinations of derivatives of power series, even when they're being multiplied by other functions. So naturally, it stands to reason that this method of combining derivatives of things together is going to lead to a way to solve differential equations. Okay, specifically, when the coefficients in our differential equation are just polynomials, all of this works out pretty nicely. The forcing function can be pretty much whatever we want as long as it has a known power series representation. But that will be coming in the next lecture.